Hello, this is Gonhi, host of Enjoying Math YouTube channel. Starting today, whenever research gets a bit hard and I need a breather, I plan to post regular lectures covering undergraduate mathematics, university level topics, and even major courses in mathematics one by one. I'm not following any particular reference for this from basic to graduate level mathematics Kidesu series. Instead, I will try to present things in a way that feels natural to me and hopefully to you as well. Let us assume from the very beginning that one may have forgotten most high school mathematics even. I will explain things step by step so that you can study the entirety of undergraduate mathematics and even some graduate level mathematics. First of all, for a while, I would like to talk about set. So this is the starting point of math major undergraduate courses. A set is sometimes simply called indeed a set for sure, but in some contexts, it is also called a collection, and in others, a family. In practice, we will not distinguish these terms in any deep sense. Depending on context, the wording may vary slightly, but we will often use them as synonyms. In short, what are these objects? They are well-defined gathering of things, collections for which what is being referred to is unambiguous according to clear criterion. So that we might simply say these are definable objects. Who have the clear, well-defined gathering of indeed things. Okay, now whether a given criterion is surely sufficient raises deeper issues in axiomatic set theory, for example, the ZFC axioms, but we will not set such topics aside for now because they are not strictly necessary for developing the material here. If a criterion is presented, we will simply think of the collection of our objects, satisfying it as a set, and we will regard membership according that criterion as a clear matter of true or false. For instance, the set of people. A set of people who are at least 170 centimeter tall, or one might think as a non-example that set up handsome people. Under some criterion, so can both be treated as set, might be, but by convention we might treat handsome people is not well defined because it could depend on the context for each individual. By convention, by the way, we usually denote sets with uppercase letters. For example, if a set has elements -1, -2, or +2, 4, 5, we might write capital letter A equals negative a collection of negative 1, 2, 4, and 5. Then we write negative 1 is the member of the set A to indicate membership using the standard symbol, and 0 does not belong to set A to indicate that 0 is not an element of the set A. More generally, when a set is given, we may describe it as a collection of X. The notation that specifies the condition that X must satisfy inside braces is often called set builder notation, such as B is declared as a collection of X satisfying the condition that depends on X with the brace. Many sets are defined in this way. Also, elements need not be numbers. For example, if C, the set, consists of 1 and 2, we use the term power set. So usually it is written as P of C. So this is indeed a set of sets. The set whose elements are the subsets of C that use 1 and 2 as possible elements. So for example, this set consists of the empty set, and it also has the element with the singleton set including only 1 and only 2, and it also contains the set C as an element. So this is the collection of the R sets of C that demonstrate that the set does not need to be the collection of just numbers. Because we have gathered sets together, this forms a set of collections, namely the power set of C. Of course, we are often interested in familiar sets such as the natural numbers. So usually denoted this way. Sometimes written in such a way, a small vertical bar in order notation, we denote it with this vertical bar with n. Some books start this notation starting from 0, but some contexts we start from 1 as a smallest, like the natural numbers. We will not worry about this distinction here much, so it's not a big deal in some sense. We also have the integers denoted usually by z. So this includes 1, 2, 3, 4, but also 0, also negative integers, and so on. They also, by the way, the set of integers include -1, -3, which are called negative integers. Later, when we discuss algebraic structures, we will consider Q, the set of rational numbers. So usually written as Q over P, where PQ are our integers, and the denominator must be non-zero for each. The set of real numbers is usually denoted by R with also vertical bar. R, so collection of set of real numbers. And finally, C with the vertical bar denotes the complex numbers. So each of these will be defined and studied carefully later, depending on each of the mathematical very interesting structures. For today, I only want to mention that these sets exist. One of a very good exercise using just these definitions is to think about rational and irrational numbers. A rational number is a number that can be expressed as a fraction p over q or q over p. A number that cannot be expressed in that form is called irrational. One can view the real numbers as consisting of rationals and irrational together. though we will later give a more rigorous definition of the set of readers in analysis. As a classic exercise, consider the number square root of 2. It is the positive number whose square is 2, proving that square root of 2 is not a rational number. That is defined as x squared equal 2 and x it must be positive. So this helps you reflect on the definition of rational numbers. With sets in hand, let us also discuss how to form new sets from old ones. Strictly speaking, one can develop or disform axioms of set theory. However, as mentioned, we will not insist on those foundations, at least right now. Let's consider the following definition. So X, a universal set. The ambient collection. Suppose A and B are subsets of this set that we usually denoted by this notation. So this means A and B are all included in X as sets and could be exactly the same. We define the concept of the union as A union B, and this is also the common notation in mathematics that we'd like to define the left-hand side in the following way. So we collect the elements inside of X that satisfies either X belongs to A or X belongs to B, like this. And we also define the concept of the intersection. A intersecting B is defined as the collection of the elements in the universal set satisfying two conditions belonging to each of A and B together, like this. And we also commonly use the concept of complement of the given set. So a complement is also defined as the collection of the elements inside of the universal set that does not belong to set A. And finally, we also define the concept of the equality for the set. So let A and B are subsets inside of the universal set, and we'd like to say two sets are the same in the case that A belongs to B as a subset and also B belongs to A also as also subset simultaneously. So you can also write as a thus for any elements in A, such an element should be the element of B, and also if, let me just use the different notation, Y belongs to B, also then such an element should be the member of the set A. Then we will say two sets are the same. Although this seems just we repeat the same idea, which is quite intuitive, I wanna state it carefully in a sense that this would be very sufficient to describe very complicated logical statements, and we can dig through or very like the deep logics in a way that we can understand the mathematical structures. So now let's also talk about three sets together as a proposition. So this is very first proposition in this Gidesu from basics to graduate level mathematics. So we now start from three sets. Let A, B, and C are subsets inside of X. So we'd like to show as our first proposition that we take the union between B and C and then take the intersection with this, the union, and we'd like to declare this is, as I said, same as A intersection B union A intersection C. In many middle and high school texts, one shows this with a Venn diagram. You draw the universal set as a rectangle, for example. So draw the universal set like this. And draw for each abstract sets set by set like that, and then just fill each of the regions correctly. So let me just copy the same thing. Oops. And what you can see is that on the left hand side we first take B union C. So let me shade that region like this, and then intersect with the set A that will give us this part, which yields the portion of A overlapping that shaded region. Intuitively, this matches the right hand side where we first take A intersection B, so here, and then we also take A intersection C, and then their union. The two shaded areas coincide. However, this is only the picture. So for the mathematical justification, so intuition is not sufficient. So especially in university mathematics, where we must learn to write proofs, just showing a picture is not enough. We should practice writing proofs using the definitions. This is, in my view, extremely helpful for learning mathematics. So let us verify the identity using only the definitions given above. Since we have already defined what it means for two sets to be equal, we will show each inclusion in turn. We must show that each sets are subsets for each other and also converse. So I often abbreviate to write fully as need to show. So this is simply just written as NTS. So I think this is very also common for mathematicians. So first we need to prove, NTS, we need to show A intersecting with B union C is the subset inside of A intersecting B union A intersecting C. And then we should prove the reverse inclusion. Unraveling the definitions, you can see, let me also write down the reverse direction as well before proceed to further argument. So this means, equivalently speaking, so if you choose by the definition, if X is the member of the following set, A intersecting with B union C, this manner, so this means that X belongs to A and either X belongs to B or X belongs to C. So equivalently speaking, this can be also rewritten as X belongs to A and X belongs to B, or X belongs to A and X belongs to C. By definition, This means that x belongs to A intersecting B, or x belongs to A intersecting C. So hence x belongs to A intersecting B union A intersecting C. This converse inclusion is already proved in the same way. Thus, both conditions are satisfied simultaneously, and the proof is complete. Some books mark the end of the proof, by the way, with a small square, like this. Some of the textbooks use QED. It's a Latin. Other identities can be tried in the same fashion, and I recommend practicing them. For example, you can also practice A union B intersecting C is same as A union B intersecting A union C. The complement of A union B is same as A complement intersecting B complement. The complement of A intersecting B is same as A complement union B complement. And I will leave all this as an exercise. These can be all verified directly from the definitions. It's straightforward. With the definitions above, we can expand the statements and check them line by line. You can also conform them with Venn diagrams. But let me add a few more definitions and then wrap up the basic discussions of sets. So we'd like to define the concept of the power set. So given a set A, P of A is indeed the collection of B, that is the subset of A. The collection of subsets of A. Because we will use this concept often, I repeat the definition here, and this is called the power set of A. And we also define the Cartesian product. So given two sets A and B, we define A cross B, the set of the Cartesian product, as a collection of the pairs AB, where A belongs to capital A, B belongs to capital B. The set of the ordered pairs with the first coordinate in A and the second one is in B. As an exercise that requires no new concepts, as follows. If A has exactly n elements, then show that power set of A has 2 to the n elements. For those starting a mathematics major, I recommend doing such exercises carefully. This helps you see where and how axiomatic assumptions come into play and build useful habits in rigorous reasoning. Now, using these ideas, I would like to discuss the notion of a function. Many have heard the term But if I ask hundreds beginning second year students to give a precise definition of a function, I'm not sure how many would be able to describe correctly. When asked what is a function, since we are asking for a mathematical definition, the answer should be a noun, and in our correct development, the current development, it should be a set because sets are the objects we have. So naively but rigorously, a function is an object defined as a set. Let us define it here together. To define a function, we start with two sets A and B. Given two sets A and B, by our earlier definition of Cartesian product from sets A and B, we can form A cross B. So that we can call a certain subset of A cross B a function. So we have certain subset S sub f inside of A cross B, and let me intentionally skip to write the equality notation here. So satisfying for each element there exists the element B inside of the capital B uniquely such that the pair A comma B is the element of S sub f. So it looks quite abstract, but this gives the rigorous definition of the concept of the function. So with the picture, we have the set A, and we pick up one element, say small a, and there's another set, capital B. Then we'd like to map via the function f for each of the elements from the collection left hand side. So this element B is small f of A. So you can see that once we pick each element small a from the set capital A, there is exactly one corresponding element inside of the capital set capital B, which we denoted this guy by f of A. We often depict this by arrows from elements of capital A to elements of capital B. Here we call the set A the domain, the set B the codomain of a given function. And we also have a concept of the image. This is the collection of the element B written by f of A for each element from the domain. So let me add one more picture for this concept for the function. So we just collect all possible elements. Here. So usually we say this is the range. Or the image. So either one are used frequently in any context. So now just as we perform operations on sets, we can consider corresponding statements for functions. call the next result as a proposition 2, second proposition. So suppose a function f from a to b is given. And let us take two subsets in the domain, say call A1 and A2. So we know that A1 union A2 is again a subset of the domain. We can consider the image of this set under this function, so that we can consider A1 union A2 and take the image. Of course, this is defined as what? We collect all possible function values whose x belongs to A1 union A2. Then it's not difficult to check this set is the same as f of A1 union f of A2. However, if you take the intersection, equality does not hold in general. So all you can guarantee is the one-side inclusion in this way, not equal. And proofs are just exercise by using the definitions. For beginners, these are excellent exercises because they help develop a feel for using definitions. Let me add one more topic before closing this video: the inverse image. Suppose we also have just an arbitrary function. So given f from a to b, so that we can draw a picture with A on the left and B on the right, and we now take a subset B1 inside of the codomain. So let me draw the picture like this: BA, B function, and we have subset inside of the codomain. So what we wanna do is we wanna define the concept of the inverse image inside of the domain. So picture hopefully give you some clear intuition that this set is described as just a taking in the inverse of it. We are not saying there is an inverse function, but it's just a notation. So in order to virtually describe, so let B1 as a subset in B, then we define as a notation f inverse of B1 as the collection of elements in A satisfying what? F of x is the element of B1. We collect all of it and call the inverse image of f under B1. Which is significantly used everywhere in mathematics. So unlike the behavior of images, inverse images preserve both unions and intersections. So let's just make it as a third proposition. So let f from a to b be a function, and we have b1, b2 as a subset in the codomain. Then first we have the inverse image of b1 union b2. This is same as inverse image of b1 union inverse image of b2. And this also holds for the intersection. So b1 intersecting b2 inverse image does not change undertaking the inverse image. And this even holds for the complement. So if you take the complement and take the inverse image, then you can also start from the inverse image first and then take the complement. They are the same. So those are also exercises that I highly recommend you to check all of this only by using the definitions. These are extremely fundamental operations that are used throughout mathematics. If you plan, again, to study mathematics seriously, I recommend trying all of this on your own and learning from the procedure. That is all for this video. Thank you for watching.